let's imagine that I have a vector field F and a path C. And just for the moment, let's think about this vector field F as giving a force. And so I have a path through this force field, right, of maybe an object in motion. And what I'm going to do here, I'm drawing a 2D vector field, but everything I'm going to say in this video holds for 2-dimensional vector fields and 3-dimensional vector fields. It's just easier to draw one in 2 dimensions. So I'm thinking about this as an object in motion through a vector field of force. And so let's imagine that I took a point here, and I wanted to talk about the work done as I move from there to over a small increment, right? And we know that work done over a small enough increment I could approximate as just the amount of force times the straight line distance I moved in. And so if I chop this up into small enough little delta s's, I can pretend it's a straight line. And so it becomes a matter of how much force is being applied in the direction of motion. And so this vector here is the force vector at a point in question. And then I could think about the direction of motion being the unit tangent vector. And that would give me a picture that looks something like this. So I have that red vector, F. I have the unit tangent vector indicating a direction of motion that's 1 unit long. And the part of the force I want to consider is the component of force in the tangential direction, right? The length of this vector. And so I want to know that length in purple, so I'll mark it with a question mark. So I want to figure out what question mark is, and fortunately, we know that the angle between 2 vectors is an easy thing to find. And so the cosine of that angle between 2 vectors is question mark over the length of the red vector, which means question mark itself is this. And every time I see a magnitude times a cosine, I'm thinking dot product. Well, t is the other vector in question here, whose length is 1, so I can sneak that vector in here. And there I have that the amount of force done in the tangential direction is F dot t, and that's actually something we saw before, and we could actually talk about that as a vector projection if we wanted to. And so what I have is the work done over a small increment, a small delta s would be F dot t delta s. And so if I wanted to approximate the work done as I traveled from a beginning point to an ending point, well then I could just chop up my path into small delta s's and add all those works together. Well, how do I go from an approximation to an exact value? Well, I take a limit as n approaches infinity. And this is the limit of a Riemann sum, so this defines integration. So this is what we call the line integral of a vector field. And so notationally, it's an integral over the path C of f dot t ds. That is what we call a line integral of a vector field. Okay, so how else could we write that? Well, we could reimagine that as f dot dr ds, just another way of writing down big T is dr ds, and now times ds here, the differential operator, which lets me write that down as just f dot dr. So these are all ways of defining this line integral through a vector field, but this last one gives me a chance to have a good calculation formula. So my final equation I'm going to write down is that I could think about this as the integral from a to b of f of r of t, right? I'm evaluating now my force, my vector field at every point on the curve, and I'm pointing off camera now, but for every point on this curve, dot dr dt dt, right? Using the idea of a substitution on dr, replacing it with dr dt times dt, and that lets me define, or excuse me, have a calculation formula for the line integral through a vector field that we just discovered. I like to talk about work when I'm getting started on this, but this works for any kind of vector field. This is the definition of a line integral of a vector field, and we can use any of this notation, and this is our calculation formula, and we'll see that in our next example.